everybody to the next to last webinar, and you can see the title, so not to take time, I'd like to focus on the collaboration. We're pleased to have David from Quadridox, which is a spin-off company that was from Joel's lab, spun off 2 years ago, and most importantly, Chris Gregory, whom we all know, that has been working with Joel for the past 6 years and is an active member of the Alert IAB. With that, I'd like to hand it over to Joel. Thanks.
All right, so thank you, Amel, for the introduction. Today I'm going to be talking about hybrid X-ray transmission plus diffraction systems for aviation security, and I put that ominous or exciting and beyond at the end. As Amel said, I'm a professor at Duke, and my co-presenters today are David Coccarelli from Quadridox and Chris Gregory from Smiths. We'll get a chance to chat at the end. But needless to say, it is not just me and these two who are responsible for all this. And so I just wanted to take a second and thank or acknowledge my university collaborators, Anuj Kapadia and Michael Game from Duke, along with Josh Carpenter and Stefan Stryker. We have a great collaboration with the University of Arizona with Professor Amit Ashok's group. And the industry partners for this talk are Dave and Chris. And funding for this has come from DHS, from Alert, and from the North Carolina Biotech Center. So since this is an ADSA related talk, I figured I'd go with the so what, who cares start. Not going to belabor any of this. The point of the rest of the talk is really going to be to describe it. But the general space that I'm interested in working in is in the detection of concealed items where that concealed item has a particular material characteristic as opposed to a shape that we're interested in being able to determine. And this shows up in a number of different problems. For example, in baggage screening, you might want to be able to scan bags faster with better material specificity. CBP has need for more sensitive technologies for detecting contraband. In particular, opioids is an example that's a hot topic currently for international mail. And medical imaging is very similar. In the bag is analogous to the tumor or the cancer in the body. In particular, medical imaging needs better soft tissue identification or differentiation. And so the solution that we've been working on is a hybrid X-ray transmission and X-ray diffraction system. And I'll unpack that over the next few slides. But what we are excited about is being able to realize improved detection performance, particular focusing on lower false alarms in the security space, but in the medical space, kind of this improved sensitivity and specificity. It also, through this better material specificity, allows for decreased divestment or the need to remove the item of interest at all. We hope to be able to expand the threat space now in the security jargon, for example, including the region of responsibilities to be extended or looking at HMEs, potentially catching the cancer or malignancy earlier than would otherwise be possible using conventional imaging modalities. But also reducing the dependence on human operators and making things more automatic by virtue of this additional feature provided by diffraction. An overall reduction in the cost of operation of the system is also a target as well. And so for the systems, at least in my lab, the technology readiness level goes from anything from 1 to 7, and we'll show a couple that are kind of in the mid-tier today. So with that, I'll jump right in. So I wanted to kind of motivate this idea of the hybrid transmission and scatter system based on a couple studies that we've done over the last number of years. So on the left here, let's see, I'm going to make my mouse a little bit more visible. On the left, we show what we call the scientific prototype, which is a coated aperture X-ray diffraction tomography system that we built in collaboration with Smiths. So exterior, it looks like a Smiths 6040i system, but the guts have been replaced with our coated aperture X-ray diffraction tomography system. With the result that we end up with this nice modular small footprint system that allows for full tunnel coated aperture X-ray diffraction tomography. And just as an example, in the middle here, I show two images, one with a bag with a laptop and some organic bulk thing. The The red box here is placed by the diffraction system that was confirming something that it didn't want to see, ammonium nitrate here, or clearing an alarm, which was based on the presence of a water bottle also placed behind the laptop. So we've at least been able to demonstrate that there are some things that might be difficult for transmission systems that diffraction can do a great job because of the additional material specificity. In our current program under BA 1402, funded by S&T, we've actually placed this in line with certified AT2 and CT systems. And I make this designation that I'll come back to in a minute, that we've placed it in line but not fully fused. We haven't fully combined the transmission and scatter systems. But one example that we thought was particularly relevant, I showed down here on the bottom a artistically blurred version of some data coming out of an AT scanner and a CT scanner. And the point of interest is that in this particular bag, there was a block of C4 simulant, which was by all rights correctly identified as a potential threat in the AT and CT systems. But when we scanned it in the scientific prototype system, we were able to identify that this block of C4 simulant, in fact, was not an explosive based on its X-ray diffraction signature. And so this just highlights the demonstrated false alarm reduction capabilities that diffraction provides relative to conventional transmission imaging systems. The second motivation for why we might want to do this at all is based on the work that we've done in collaboration with University of Arizona, in which we've investigated task-specific information of the relative transmission and scatter systems. So task-specific information quantifies the amount of information in a given measurement or a data set relative to a particular task. So in the security space, we might want to know whether there's an explosive present or not. And you can make the most beautiful picture in the world, but if it can't answer that question, it has no information relative to that task. So to do this, we need a lot of data, and we've built an infrastructure at Duke and at Quadridox to be able to generate synthetic data for a range of different modality systems, from multi-energy AT and CT to X-ray diffraction systems. And by creating loads and loads of virtual bags, we end up with loads and loads of virtual data, whether that be virtual radiographs from single energy or dual energy systems, or virtual sinograms, or even virtual diffraction data. And with that, we can then apply the information theoretic framework and the metrics associated with it to ask questions about the amount of task-specific information present in that data. And so this histogram in the middle, it was an experiment that we had done looking at the inherent distinguishability of different materials in the transmission or the diffraction space. And so it's a histogram showing how many materials have some degree of separation between them. And I won't go through the technical details, but basically it boils down to the fact that on the left-hand side of this dashed purple line, all the materials that show up in this bar chart are better separated via CT. So their density or Z effective are perfectly sufficient that they have better separation, they're more separable through a good transmission measurement than a diffraction measurement. On the right, it's materials that are better separated from one another via X-ray diffraction. So one of the things that we took away is that there's value in each of these systems. Some materials are better distinguished by diffraction, some by CT. In addition, though, we found this interesting point that there were some materials that simply couldn't be distinguished at all in transmission and happen to end up as being reasonably well distinguished via diffraction. So this led us to ask the question, how redundant and how complementary are the different features that diffraction and CT provide? And so Amit's group at the University of Arizona did this task-specific information study where we looked at the amount of information relative to threat detection in a transmission system. So we modeled the Smith's ATIC system. We modeled the scientific prototype that I just showed you a minute ago. And we looked at the amount of information obtained by combining those two systems in an integrated way. So we combine all the information and we ask we combine all the data and we ask how much information is there. And that's this, actually they're indistinguishable, the curves are on top of each other, but we can either calculate the amount of information in each signal separately and combine them, or we can combine the data and calculate the total amount of information. And the fact that those two lines are effectively on top of each other means that the transmission and scatter signal is largely orthogonal in this information space. So what transmission does well, diffraction does not necessarily do well, and vice versa. So that by combining the two measurements, you end up with significantly more information than either system by itself. And so to kind of, at a very high level, show this relationship, I put this bar chart together where green is good and red is bad. And there are existence proofs for the Smiths, or for a number of different CT systems, either in the EDS or the checkpoint space, and a number of different X-ray diffraction systems. And the goal here is really to fuse them so that we can combine the two systems and end up with the best of both worlds and not be limited by the worst performance of either. So we want to fill the capability gaps of each system to realize enhanced detection. And we do this by the co-design of the transmission and diffraction systems so that we can end up with good throughput, good spatial resolution. We get the good material discrimination of diffraction system and the good spatial resolution of the transmission system, so that in the end we get good detection performance in this hybrid system. And so our approach for doing this and doing the hybrid data fusion is to consider the systems as more than just the sum of their parts. So as kind of general recommendations for how to do this, we've adopted the philosophy that transmission should not just tell the diffraction system where to look. It shouldn't just be where is the water, look that way, and resolve it with the diffraction. And also that the transmission and the diffraction features should not just be combined at that final decision-making detection step. Instead, what we're looking at for this hybrid data fusion is to actually design the physical diffraction system with the transmission system in mind, knowing what information it could provide you and using that to optimize the diffraction system design and execution. So things that transmission systems can do are to tell it where to look and where not to look. It can help you aggregate the photons that you collect for better SNR in the diffraction data processing. It can also give you an idea of what is or might be in the beam path. And with that information, you can either build a less expensive system or a system that has higher belt speeds to be able to be more effective in the diffraction space. The diffraction system can also tell the transmission system things like what materials might be in the beam path. And that can be useful for doing artifact reduction or beam hardening corrections. And so in the end, we've worked now to develop a design for a modular real-time full tunnel XRD module. We targeted checkpoint originally, but we're currently working on a check baggage system designed for S&T right now. And so just to be a little more quantitative, this is going to Joel's simple simulation to try and make a point. I created here a virtual bag, and we can look at that bag just in a single slice through the bag. We have a number of materials. So you can see that the bag here has some RDX in a little block or data sheet in a little block. It has a water in one place and cheddar cheese in another. If we look at the CT or the density, those values can be very similar to one another. But if we look at a threat map, it's all ones or zeros. There's either nothing there, there's a threat there, or there's a non-threat there. And so if we try and do reconstruction with the as-designed system using only the diffraction information, we get a mess. There's materials all over the place. There's a threat map that doesn't look at all like the threat map. And running at belt speed with a very economical system layout, there's just too few photons to be able to do anything really valuable. But when we combine that with the CT information, we get a much better spatial reconstruction, and our threat map about where the threats are and are not is then spot on with the ground truth shown here in the bottom. And we can do a fair bit of material distinction. So we can say that it's specifically datasheet instead of just an explosive. Sometimes we get it a little bit wrong. We mix up water for Sierra Mist, but maybe that's okay. And the fact that some degree of material identification is possible is exciting, even though it may or may not be necessary in kind of this binary detection task. So as an experimentalist, though, I always want to validate my simulation results with experiment. And so Josh Carpenter at Duke, has built our hyperspectral CT and XRD testbed to prove out some of these designs. And this lets us play around and evaluate new components and architectures. It lets us scan real bags, and it also helps us in our algorithm development. So this system that we have at Duke allows us to do full CT, helical CT, or slice-by-slice CT with multi-energy detectors. So we have an X-ray source, translation and rotation stages for the bag, and an array of energy-dependent or energy-sensitive X-ray detectors on a translation stage that can scan through. So we can measure the transmitted signal at a range of different object orientations, as well as a full angle and energy dispersive X-ray diffraction signal. And we have space in here to put whatever X-ray optics for modulating the beam or shaping the scatter as we see fit. So just an example of this, Josh had packed this box full of clothes and walkie-talkies and some pharmaceutical products, and made some very simple X-ray CT measurements and did just a very simple reconstruction. But you can see that the top box that had aspirin in it looks awful close to the bottom box that has oxycodone in it in the transmission measurements. But if we look at the diffraction measurements, you can see that the dashed lines, which are the spectra here for the measured aspirin and oxycodone, look very different from one another, and in fact are very similar to the solid lines, which are the diffractometer ground truth measurements that we had. So being able to distinguish between different drugs or different organic materials in this type of hybrid CT plus XRD system is one thing that we've been exploring experimentally as well. We've also built another system at Duke, what we're calling our XR3D scanner, which is currently in the Duke pathology lab in the Duke hospital. It was built to be able to take data for medical sample analysis, and it's limited to thinner samples, but it's a very high spatial resolution system. And so we've played around with this same drug detection challenge where Stefan placed some oxycodone hidden next to some icebreaker gum and placed it inside of some bubble wrap, inside of a box, and put it in our scanner. And you can see that in the transmission radiograph, there is some slight color difference, but again, it's unclear whether it's due to the fact that the oxycodone is clearly thicker or if it's really the different density of the material. Whereas in the diffraction image, the oxycodone lights up in this green color, which is just a false coloring based on the X-ray diffraction spectrum. So being able to do some drug detection or pill evaluation in this scanner, which takes a minute or two to make this full scan, is something that we're playing around with. But we're also looking at full 3D tomography. So you can see the little Lego John Lennon. So that gives you a sense of the size. With its radiograph next to it and a 3D tomography map that we were able to make, again, in just about a minute or so, using our X-ray diffraction tomography. So using it for depth imaging rather than worrying too much about the material specificity. We've been able to analyze a lot of different organic substances. Obviously, in the medical imaging space, everything is organic. So we can very easily distinguish between things like water or plastics, which otherwise might be challenging for transmission systems. And we've gotten it to a fairly high resolution where we can even put in some plastics and electronics and be able to distinguish some of the material characteristics in something like a cell phone. So just to sum up, we think that transmission and diffraction offer very exciting opportunities for concealed item detection. Our mantra is that the diffraction system should be tailored to the transmission system that it complements. And that proper transmission and diffraction fusion can actually yield a best of both worlds rather than being limited by kind of the worst of both worlds. We've been able to demonstrate that experimentally and in simulation. And we're currently in the process right now of designing, building, and testing a variety of these types of transmission and diffraction systems for both baggage inspection and medical scanning. And with that, I will turn the audio over to my collaborator, Chris Gregory at Smiths.
Thanks, Joel. I appreciate that. So Smiths Detection has been engaged with this type of research, working with Joel, as we said, for about 6 years. And we're very pleased with the progress that we've seen XRD take over this period of time. Smiths Detection, as many of you are aware, is is in the airport security area, but also in other regions of security. So our objective here is to find new technologies and help develop them so that they can become useful as a product later on. We've developed, obviously, transmission X-ray systems and CT systems, as you can see in the upper two right-hand images, but we also are involved in other modalities such as ion spectroscopy or millimeter wave imaging. And in the lower right-hand corner, you can see a non-airport application, which is basically a drive-through gantry scanner for either trucks, trains, vehicles, whatever the case is. Our goal is to continue this research. We have done research with ALERT and with ADSA. In particular, we did work with Carrie Rappaport and Jose Martinez Lorenzo in the past. We're hopeful that in the future we'll also be able to continue doing research with various team members. And with that, I'm going to hand it over to David.
All right, thanks, Chris, and thanks, Joel. Hi, everyone. I'm Dave Coccarelli from Quadridox, and I first want to thank ALERT for facilitating these talks. We've found them at Quadridox be a great way to bring both people and ideas together. So a little bit about Quadridox. We're a university spin-out companies with founders at Duke University and the University of Arizona. So we've been around just over 2 years attempting to bridge the gap between technology developed at the university and industry, focused now on the aviation security space. So in particular, with respect to the work that Joel spoke about, we're collaborating closely with Duke and Smiths to design, build, and test a robust implementation of this transmission-informed XRD for checked baggage screening. So as a university spin-out, the collaboration between the university and industry is one of the ideas that Quadridox was founded on. And we're thrilled to have ALERT in which to build and foster these relationships. So, as Quadridox continues to grow, it can become very easy to move further and further away from the research done at the university. But we do feel strongly that in order to maintain the forefront of novel and evolving technologies, those university relationships are incredibly important. And that is why it's so great to have these ALERT talks and to have the ADSA conferences, is it really allows us to keep our existing connections as well as grow new ones. So Quadridox looks forward to further advancing and sharing our work with this community, as well as forming new partnerships within this group. So we're also really excited about continuing the ADSA events and look forward to the new format. So with that, thank you for your time, and I'll pass the baton back to Joel.